have you experienced some of the technology improvements the division has made through work that has been done by Tommy Thompson, a senior GIS analyst for the division, and he's going to show you some interesting drone footage that he's taken down at the Coal Hollow mine in Kane County, and I'll just turn the time over to Tommy.
All right. Tommy, you got an award recently for some high thing. What was that?
So we recently received a Special Achievement in GIS Award from Esri, so the ArcGIS software that a lot of companies use. Our department has a Esri Enterprise license, and so we were recognized nationally. I think there were some 4,000 different companies, a couple hundred states, so we did pretty good. So it's a pretty big award for us, so we're super excited about it. 4,000 different nations.
Tommy and I will be going to the Users Conference in San Diego next month, and we'll actually receive that award directly from the, I forget his title, the head dude for Esri.
Yes.
Jack Dangerman.
Jack Dangerman, yes. So that'll be exciting. So yeah, there's a lot of different cities and countries that applied for this, and so it was great for us to be one of those that were selected. We went out to Coal Hollow with Priscilla Burton had invited us out, and we worked with Kirk Nichols down there to conduct the drone flight. And what they were kind of interested in is getting volumetric data, so doing a photogrammic type of flight where we fly grid pattern and we get a high resolution orthomosaic map, and then we also are able to get data like a 3D model, and that has a point cloud in it, and a digital surface model, which I'll explain to you a little bit more about those in a minute.
What's an orthomosaic?
An orthomosaic is basically, so we fly over and we took 398 shots, so we have 398 individual images, and then it mosaics those together, and then it ortho rectifies them, so it puts it in the correct place in the space, so puts it in the correct X, Y, and Z locations on Earth. So that's what that is. And then the volumetric measurements come from those digital surface models and point clouds. So just to show you a little bit of the data collection process, this is our autopilot software called the UGCS. And basically, I think I've showed this to you guys before. The drone goes up, flies its grid pattern, mowing the lawn is what we call it. And then as the batteries die, we bring it back home, and then we land it, put new batteries in there, have it continue its flight, and that's pretty much a stickless. I don't ever have to touch a stick, so I hit start with my computer, hit return to home on my computer, and I don't have to ever have real interaction unless there's something going on. So we're using this new software called Pix4D. OSM has just granted us the first license that they've handed out to any state, so we're excited to get that software. That software is typically about $8,000, and so luckily we don't have to pay for that, and we also get to work with those guys in terms of developing our drone program. So this quality report really is just kind of showing that the pixel resolution that we got for that orthomosaic map, that 2D map, is 1 inch pixels, 1.12. So we got really fine detail, and then we covered 293 acres, and so we covered pretty good chunk of land, and we did it in about 2 hours. So here is that orthomosaic that you're asking about, Mr. Chairman. And so that orthomosaic, we had the 398 images. It used all 398, and it created this 2D map that's got a very high resolution. And this over here is that digital surface model, representing red is higher elevations, blue is the lower elevations. So we get a nice little report out of this Pix4D that we can then generate and share. And then I have a quick little video to show you what the point cloud looked like. And I'll kind of just talk you guys through this. This is the point cloud. As you can see, you can kind of see each of those individual points. It's almost like a transparent. But the point cloud is what gives us is elevation data. So this point represents this elevation, this point represents this elevation, and that is basically come out of parallax. So that photogrammic process, each image kind of overlays. We take them on a 70-degree angle to get kind of these side profiles of those. And then we're actually able to, this is one of the default outputs. We take all those images, put it into Pix4D, and we get this point cloud. So the point cloud is very beneficial, but again, here's this the orthomosaic high resolution 2D maps are very beneficial as well to do basic site surveys. You can determine what's on site, get a snapshot in time. Don't necessarily have to wait for satellites or for airplanes to come do a flight over. And so right here, I'm just kind of zooming in on Augur. So their Augur is what they're actually using right now. Is they're doing some Augur mining. It's pretty impressive. We can actually even see the blades. This Augur bit right here even seems like it's maybe a little bit. Maybe that's a shadowing. I'm not quite sure, but you can also see the pile of discarded Augur bits and blades. We even get the forks on the forklift. So we get very, very high resolution. That's what the orthomosaic provides to us. And then again, when we're doing volumes, we can't really use a point cloud because we don't have that surface, so we use that DSM, and that surface model takes each of these points, draws a line, and says, here's your surface, point line, surface, and it did it 40 million times. And so with this, you can clearly see these stockpiles, and we can get these volumes from it. And so let me just kind of speed this up a little bit. So you get this incredible detail. You can see, that coal seam right there. That's almost makes the equipment look like toys out there, but it's definitely not. They're very large. It's a massive site that we were able to cover. So what I did is I basically drew polygons around each one of our volumes, and then those polygons I then estimated volumes for. So what you're seeing is the cut volume, and that cut volume is basically saying, hey, if we were to lop off this pile from the land, then we were going to get a flat surface, and this is how much material it would be. The fill is basically the reverse, saying, hey, here's your highest point, we're going to fill up the bathtub, and that's how much material that would take. And then there's an inherent error. It's just like any other statistical analysis. So there's a volume difference, so it's plus or minus usually about 50 cubic yards to 100 cubic yards. This one I think was about 75. So here we have a couple different algorithms. So I used a triangulated algorithm for estimating volume, and we also have this average, so we can get an average. We can make it custom. We can make a fit plane if we want a certain slope. We can do the highest point, or we can do the lowest point. So those are kind of the different algorithms we use for estimating volumes. So the reason, like I said, we did this was kind of to look at some of the volumes that they already have. So we have their as-built or northeast facility map. Just zooming in right here is where those stockpiles were proposed. And so you can see right here, the stockpile is got 19,000 cubic yards for this purple arrow. And with ours, we came up with about 16,000 cubic yards. This yellow arrow says they have allotted 125,000 cubic yards, and we found that they have 104,000 cubic yards on site. And then this red arrow shows that they have the capacity of going up to 17,000 cubic yards, and this blue polygon shows 9,000. So you can see they're within their as-built plans. So we've begun doing the file sharing process with these guys. We're gonna obviously rely on their surveyor to go and ground truth to the data. They have a surveyor and a surveyor stamp, and so we want to make sure we're working close with those guys. We're gonna compare our volumes with that surveyor, and then hopefully we're within each other's volume estimates, and if not, then we'll kind of discuss those next steps. So it's been important for us to kind of work with these industries and operators as we develop our program, so that way we can kind of develop our program in a way that they agree with, and that maybe they have ideas that I don't have. And so it's been great to work with Cole Hollow and Priscilla on this. So thanks for your question. Thanks for your time. Any other questions?
Board members, questions on the left, starting with Rich, and we'll just go all the way down.
I'm very impressive. I'm just curious about the accuracy. What is the plus or minus you get on an elevation relative to whatever datum you're working off of?
So that's one of the nice things about this PIX40 report is I have it up because I was assuming this question was going to come. So we basically, in the statistics, they give us an RMS error, so root mean square error. So I think we are within, this is in meters, so for our Z value, we're within 2.5 meters of accuracy. Y, we're within 1.7, and with our X, we're about 4 meters off. So we're pretty confident with our location accuracy, which then translates into some of those volume accuracies. And so,
And you had mentioned an absolute volume as your plus or minus. What would that be as a percentage of the stockpile?
it's typically about 1% is what we've been finding, but that's kind of why we're working with that site surveyor, just to kind of make sure that the ground truth data kind of shows that we are within a ground truth plus or minus 1%.
Thank you.
Yeah. Steve?
The pixel was it 1.25 inches or?
Yeah, 1.12 for the site, and it depends on how high we fly. So if we fly closer, we're gonna get better resolution. The higher we go up, the more coarse the resolution.
So you can see something as small as, say, 6 inches, maybe 6 pixels, or is that?
So 6 inches would be 6 pixels. Yeah, that's basically what it would translate into. And so when we do some of our image classification, we're actually finding we actually have to dumb down our data. So we have to image classify off of about 6-inch pixel resolution. Otherwise, we're classifying shadows and sticks and other things that are difficult to use AI to classify out as vegetation, non-vegetation. So, yeah.
For those questions, on this side. Chris?
Just a couple of questions. If you have a dispute with an operator over volumes, which one would you rely on? Would you rely on their data or this side?
Yeah, so right now we're kind of going through that process. Obviously, I think the tradition's going with their data, and so we're going to keep going with that. They have a paid surveyor on site. They have a surveyor stamp. We don't have a surveyor. This is kind of one of those ways where we're trying to get similar data to what a surveyor would get, but not at the same cost, or taking the same amount of time. So we would obviously rely on the operators.
I would assume the goal is to, at some point, get to the point that you could use this flyover to verify and use as, in a situation where an operator says, okay, I've got 4,000 or 45,000 tons of topsoil here, you come up with some other number. At some point, you want to be able to use this information and say, no, wait a minute, we're not in agreement here, we've got enforcement action, we want to use our own data. Isn't that?
Yeah, I think I would rely on my boss to tell me what to do with it.
I think I'd rather look at it as a possible enforcement action. I think it's, if we find great discrepancy between what we're seeing and what they're telling us, it's just another step in saying, well, can you justify the numbers you're coming up with? Because we're coming up with something different.
Yeah, well, I understand, I can see where this could go. In fact, I see one of your inspectors out here in the audience, I'm thinking, hey, why do you need an inspector on the ground?
Yes, and that is a very common fear, I think, too. It's not well placed because we take even these high resolution ortho images and we have a 3D model. We were actually working with Wayne Western over Lisbon Valley. There was a black kind of donut on the ground, and I thought it was a barrel. He thought it was a tire. This is why we need an inspector to go out there and look. But it does help us prioritize, areas where inspectors could go look. So it'd save us time in inspections by being like, hey, we're not quite sure what this is, but we can mark it on a map, and then we give them a little map that they can navigate the site with and focus on certain areas and not waste their time on other areas.
And I would say that a drone is still artificial intelligence. I think we need on-ground eyes and ears to be able to discern with real judgment what we're looking at.
Yeah, you're a drone operator too, right? So, yeah.
I think this is just the beginning of useful technology on these sites. I can see all kinds of potential for good things to be done.
Great. Right, that's great to hear. But yeah, as John said, I think as we develop our drone program, I think we're going to keep you guys apprised, attorneys apprised, industry apprised of what we're doing. Kind of make this a collaborative effort before we try to say, yeah, we're going to use our numbers over yours or in concert with yours. So we've got a lot of work to do still. So we're just at the technology part, and then you guys will help us with the policy and legal part. So.
Thank you. Other questions? Seeing none, Tom, thank you very much.
Thank you.
Thank you very much, Tom. Appreciate that. Just a couple of things that I'll mention before we finish up that are coming up in future calendar. I think that I've reported to you this major study that the Groundwater Protection Council is doing that we've been working on now for 2